Okay, so that's pretty hard to dispute, in my opinion. This is the data. A lot of times you'll see talks that are a little old. This has this is from Jim Hansen from NASA. His updated values for the last several years, just so you know what the trend looks like in the last few years, as opposed to reading about debates that may have happened 5 to 10 years ago. There's no sign of this trend decreasing. And he puts this 95% confidence interval around what he estimates to be the error in this estimate. It is a global average of all the temperatures at the surface of the Earth. And this has changed. This confidence level has changed, of course, as there's more and more observations globally, as the way they interpolate between observation, I think, is getting better. It's a very careful analysis of what the value is, or what the uncertainty is on this estimate of this global temperature. So reducing all the weather down to this one annual temperature, which I think for a lot of people is hard to get a sense for, and it was for me for a long time as well. It's not an easy measurement, but it's doable. So, so this is my favorite thing to show people. I think when it comes down to this whole, what does it happen to the CO2 and the temperature, and how are they linked? This is from, well, you're not seeing any of these references, but this is from a nice paper in Science by Pelkowski, where they looked at the last approximately 500,000 years of trapped gases in the Vostok ice core, and can estimate the CO2 concentration in those trapped bubbles, as well as the temperature. And what you see is that the temperature when it formed, and what you see is just very strong relationship between the CO2 in the atmosphere and the temperature. And it just goes back and forth, and it's been changing like this over, well, this is evidence for 500,000 years or so, and there's evidence that it goes out beyond the millions. It's that period of glacial and interglacials that we're familiar with, ice ages. Okay, so you look at this and you say, well, we know what the atmosphere has been doing then in terms of its CO2 for the last approximately 1 million years. And we're pushing it now up to this region here. And I have to move this icon. His question mark was here. We're increasing 2 ppm or so a year. So this is 10 years later, so we're up here. So we're very dramatically pushing this outside of a realm that we have any sort of recent historical or geologic understanding of how it's going to behave. So this to me says, you know, what do you call one a cause, one an effect? Something's going on here between temperature and CO2 that's pretty indisputable. What we think caused these in the past, however, are slight changes in the positioning of the Earth with respect to the Sun. So let me just bring up that one, solar changes, which you'll hear often. This is a stitching together of the satellite era's data. This is daily data, this variable stuff, and then averaged together for longer periods in this black line. But this is a general trend we've seen. These are stitches together of various data sets, very carefully, where some of them overlap to cross-calibrate for periods. So we think this is an actual accurate, self-consistent data set of what the sun is, since we put satellites out in space, measuring that the energy from the sun, looks like. And it does have this periodicity that everyone knows about in earth science. This is 11 or so year period of the sunspot activity. And that shows up actually in climate signals. So we know that this is an important forcing, but if you actually just do the energetics like that cartoon version I just showed you, how much energy difference this is in terms of what reaches the Earth and therefore warms it, it comes out to these units. Might not mean anything to you, but it's equivalent to something on the order of 1/10 of a degree Celsius. Not very significant. This is something approximately 10 times weaker than we know the CO2 forcing to be since pre-industrial times. So we know, and we don't see any trend in this in the sun for the last, whatever, 20, 30 years. So we have our eye on the sun, even though our moms told us not to, and we've been doing this for a while, and we think we understand what's going on. Granted, this is a small interval of time since we've been cognizant of this and able to put out measurements into space, so we can watch this very carefully. So this definitely can't explain that temperature trend I just showed you. This is approximately, well, it's expanded, right? So if we put this in the same scale, it would be this part of this. There's no sign that the sun is doing anything like that. Okay. So this is going to be dubious because it's a movie. And this is not a laptop. But all right, sorry about that. It is on the, yeah. So let me just start by saying you'll hear a lot about this albedo effect. Albedo comes from the Latin root for white, like albino or albumin, the egg white protein. And it's just a bulk measure of how much light is reflected away from a body. So it's basically like a reflectivity. And one thing you'll probably understand just from looking at satellite images of the Earth, you'll see that the oceans are very dark, meaning not a lot of sunlight being reflected off those things to your eye from satellite. Whereas snow, a snow covered or a polar ice cap, for example, or these clouds here, you can't really see this image, unfortunately, because of the projector, but this is an image of, oh, it's gone. The image of California from satellite that's on the sidebar of all these slides, just to let you know. And those white clouds out in the ocean, that marine layer that's so foggy here that dominates our weather so much of the year, is very bright from outer space, meaning it's reflecting a lot of sunlight. Sunlight that otherwise would have reached the dark ocean and entered the system and warmed it. So those clouds are very important, as well as these polar ice caps. And this was an animation, might not work, but this is an animation, that's all right. This is an animation of the last, say, 25 years. A satellite, again, estimates of this northern hemisphere. Well, this is sea ice, and this is land ice, right? And this magenta line is the average over those 20-something years. And what do we got here? Can we move this? No. So do you have the other way to look at these things in here? But this to me is an important one. This doesn't rely on any modeling, any computer modeling. This is strictly, again, observational. And we see that this is dramatically shrinking, this area. Unfortunately, you're not going to be able to see it, but you can actually find it on the web quite easily. Okay, go for it. This is a snapshot in September, towards the end of the summer season in the boreal, in the northern hemisphere. And what you see is that this has just been gradually shrinking over the past 20 years. Again, the satellite era, we've been able to look at these things a lot more carefully, quantitatively from space. Thank you for trying. We might get it here in the discussion. So, just wanted to, this to me is some of the most convincing arguments about this are observational ones. And here's the thing about it. So we said, the sun's been forcing it. In the past, something's been changing. This small change in solar radiation somehow gets amplified in the system and causes these large temperature changes from ice age to interglacial. And what we think that is due to these feedbacks. And so this is why I just want to show you an example of a feedback. This is an ice albedo feedback. So you can imagine the warmer the planet gets, the smaller this cap gets, right? The sea ice gets. And what does that reveal? It reveals more dark ocean underneath it. So the difference between sea ice and no sea ice is tremendous in terms of its albedo, right? Bright white, dark ocean. So you move that, and now all of a sudden it's warmer, and now there's more area that can absorb sunlight, therefore it's warmer, ergo, so it keeps positively reinforcing itself. So people think that this has been a large, and specifically in the northern hemisphere, this has been a large forcer on various changes that have occurred in the past that get amplified in these large temperature swings between the glacial and interglacial. So this is a cause for a lot of concern in climate scientists. Are these feedbacks, where we're not just talking about, well, the energy changes so much, temperature changes, well, what does the system do in response? And that's where all the excitement comes in. That's where the fun comes in, figuring all this out. Okay, one positive one, just to try to be more of a less of a